Hi guys, happy St. Patrick's Day. I am going to write up the solutions to section 2.1 exercise 14. This will be the first of 3 videos because there are parts A, B, and C, and I think it'll be useful to have a separate video for A and for B and for C. So let V and W be vector spaces. Let T be a linear transformation from V to W. Part A asks us to prove that T is 1 to 1 if and only if T carries linearly independent subsets of V onto linearly independent subsets of W. All right, so this is an if and only if, so we need to prove 2 implications. We'll first prove that if T is 1 to 1, then T carries linearly independent subsets of V onto linearly independent subsets of W, and vice versa, that if T carries linearly independent subsets of V to linearly independent subsets of W, then T is 1 to 1. So, proof of part A, we'll start with the forward direction. So that is, we will suppose, or rather, this is sort of our assumption, that T is 1 to 1. Okay, then we're going to prove that T carries linearly independent subsets of V to linearly independent subsets of W. What does that mean? That means that if you have a linearly independent subset of V, and then you apply T to each of the vectors, you end up with a linearly independent subset of W. So that's actually an implication in itself, that if you start with a linearly independent subset of V, then T of those vectors is linearly independent. So we will suppose that I will call my set S, and I will call my vectors U1, U2, up through UK. Suppose this is a linearly independent subset of V. We want to show that T of S, namely the set consisting of the vectors T of U1, T of U2, etc., is a linearly independent subset of W. Right. So we shouldn't start with a linear combination of the U vectors equal to 0. It's true that if any linear combination of the U vectors equals 0, then you could conclude something about the coefficients. That's what linear independence means. But that's just something that we know about S, that if we ever were to encounter a representation of the 0 vector using the vectors from S, then you could conclude something about the coefficients because there's only one way to do that. But we already know that. We don't need to suppose that we have 0 represented using the vectors from U. What we do want to show is that this set, T of S, is linearly independent. That means that we need to show if you start with a linear combination of these that gives you the 0 vector, then the coefficients must be 0. We want to prove that implication, that if 0 can be represented using these vectors, T of U1 through T of UK, then all the coefficients must be 0. So let's start there. Suppose A1 times T of U1 plus up through AK T of UK is equal to the 0 vector we'll specify from W for some A1 through AK in the field. Our goal will be to show that each of those AIs must be 0. We don't start knowing that they are 0. All right. So if we know that this equation holds, what can we do? Well, we want to relate this ultimately to a linear combination using the vectors from U, since we do know that that set S was originally linearly independent. So we can use linearity of T. Then, if this equation holds, then this equation will also hold, because that's precisely what linearity gives you. That if you scaled T applied to a vector, it's the same as T applied to the scaled vector. And if you add T of a bunch of vectors, you get the same thing as if you added all the vectors together and then applied T. So that means that T of this thing is equal to the 0 vector now. And mind you, that does not tell you anything about these vectors, or this vector equaling 0. That linear combination inside of T now doesn't equal 0, at least not yet. We haven't shown that yet, but we will be able to conclude that because we know now that T applied to that vector is 0. Well, if T is 1 to 1, then we know something about the vectors that get sent to 0. Let's spell this out. We'll say that since T of this thing is equal to 0, this means that the vector, the one linear combination that you get here using the vectors U, is in the null space of T. Because the null space of T is exactly the set of all vectors in V that get sent to 0 when you apply T. But if T is 1 to 1, then the null space consists of only a single vector. By theorem 2.4, since T is 1 to 1, the null space of T consists of only the 0 vector from V. So what we know now is that we have a vector from the null space, but there's only one vector in the null space. So this vector here must be that 0 vector. Thus, A1U1 summed through AKUK is now equal to the 0 vector from V, and that's useful because we know that S is linearly independent, so the only way that we can get 0 as a linear combination of these vectors U1 through UK is the trivial way. Since S is linearly independent, each of these coefficients must be 0. But these were the coefficients that we started with when we were representing the 0 vector in W using the vectors from T of S. So we started with arbitrarily chosen A1 through AK that gave us a representation of the 0 vector, and we ultimately concluded that those coefficients would have to be 0. So we can conclude that T of S is linearly independent, which proves our first implication that if T is 1 to 1, then if we start with any linearly independent subset of V, T carries it to a linearly independent subset of W. Great. So now let's try to prove the reverse implication. So here now our assumption will be that T carries linearly independent subsets of V to linearly independent subsets of W. So if ever we encounter a linearly independent subset of V, then we'll know that T applied to each of those vectors will form a linearly independent subset of W, and we will want to show now that T is 1 to 1. we will show that T is 1, 2, 1. All right, there are a few different ways we could try to do this. One method would be directly. We could try and show that if T applied to one vector equals T applied to another vector, then those vectors would have to be equal. But we know something about T carrying linearly independent subsets to linearly independent subsets that is related to representations of the zero vector. So maybe we'd like to try to use this theorem 2.4 again in the other direction. If we could show that the null space of T was equal to 0, then we would conclude that T is 1 to 1. So that's going to be our method here. To do this, we will show that T is, we'll show that the null space of T is equal to only the zero vector, or the set containing the zero vector. And by theorem 2.4, we can conclude that T is 1 to 1. So we've shifted our goal now. Now we want to show that the null space of T is equal to the set containing the zero vector, and that will finish our proof, since we already know now that theorem 2.4 will give us the conclusion we were aiming for originally, namely that T was 1 to 1. All right, so we will show that if T carries linearly independent subsets of V to linearly independent subsets of W, then the null space of T must be 0. All right, we want to show that the null space of T is equal to 0, the set containing the zero vector. So we want to start with something in the null space and show that it must be the zero vector. So now suppose we take some arbitrary V, not arbitrary from the entire vector space, but arbitrary from the null space. An arbitrarily chosen vector that has the property that T applied to it is the zero vector from W. Well, that it's got an equation that involves the zero vector, but in order to use linearly independent, we need to unpack this. Somehow V is not necessarily a linearly independent set by itself. All we really have is that T of a single vector is equal to 0. So I guess if we could represent V using a linear combination, but we need something linearly I see. I guess we could use the fact that every vector space has a basis. So here would be a good place to say, let beta be a basis for the vector space V. Then every vector in V can be represented as a linear combination of the vectors for beta. So in particular, this V, which we chose from the null space, well, the null space is also in capital V. So that little v can be represented as a linear combination of the vectors from beta. Then V is equal to, and I'll just write it in summation notation now, equals 1 to, I guess let's say N of AI, I'll say VI for some A1 through AN in the field, and V1 through Vn from this basis that we've named. Let beta be any basis because every vector space has a basis. Then every vector can be represented as a linear combination of the vectors from that basis beta. Moreover, the basis beta is linearly independent. So now we're going to be able to get somewhere. Then the zero vector from W, well, we know that it's equal to T applied to this vector V, but now we know that we can rewrite that vector V as a linear combination of these vectors VI from the basis And then by linearity again, we can write this as a linear combination of the vectors T of VI, the transformation of those basis vectors. Well, since beta was linearly independent and T carries linearly independent subsets, two linearly independent subsets, the set T of V1 through T of Vn is linearly independent, which means this equation that we have tells us something now. If we can represent the zero vector from W as a linear combination of these vectors that we know form a linearly independent set, then we know that each of the coefficients in that linear combination must all be zero. But these coefficients were the things that we used to represent our arbitrary V from the null space in the first place. So what this really tells us is that the vector V we started with, AI times VI, well, that's just a sum of 0 times these basis vectors now, which ultimately will give us the zero vector from V, which means that any arbitrary V that we select from the null space must actually be the zero vector from V. It can't be any other vector. We conclude that the entire null space of the transformation T is the set containing only the zero vector, which, as we said, then allows us to conclude that T is 1-to-1, as we originally wanted to show. So that proves part A, that if T is 1-to-1, then T carries Li subsets of V to Li subsets of W, and vice versa, that if T carries Li subsets of V to Li subsets of W, then T is 1-to-1. See you in the next video.